Hello, welcome to our next video for Math 103, Mathematical Reasoning. We're continuing our section on personal finance. We're in section 4B. Today we're going to talk about interest, especially talking about compound interest. So let's start off with simple interest. When you loan money or when someone loans you money, people usually charge a fee. We call that interest. It's usually some percentage of the amount you borrow. And more interest is usually charged when the money is loaned for a longer period of time. So if I go borrow $100 from someone and then I pay them back $105 when I pay them back, that $5 was my interest. And it's basically a fee. I paid them just to let me borrow that money. When you're borrowing money in this situation or loaning it out, depends on which person you are, we call the amount of money borrowed or loaned the principal. So that's the amount borrowed if you're the borrower, or if you're the one loaning it, you're the investor, it's the amount loaned. That's the principal P. We'll use P for the principal. We'll see that pop up for a lot of the equations in this section and later. The annual percentage rate is going to be your yearly interest rate. We typically work with interest in yearly rates. A lot of times people just use R for annual interest rate because it's a rate. APR is kind of the more correct version of that because it notes that it is a yearly rate. So this is your yearly interest rate. We'll pretty much work exclusively with APRs, with yearly interest rates for this section. So that's what we'll see mostly. Time, T, that's just the years that you have the loan. Because we're working with a yearly interest rate, we're going to work with time in years. So this is how long before the loan is repaid. So whoever borrowed the money, how much time they have until they repay that back. And it's going to be in years. I think your textbook, if you go read your textbook and stuff, a lot of times they'll use Y instead of T because they're specifically dealing with it. It's more common in general to work with T for time. So that's what I used for our formula sheet and for my notes. So T for time, but it's going to be in years for us. We're not going to really deal with shorter periods. If someone did give you a short period, like 6 months or whatever, you could turn that into a number of years and still use it in these equations. So you could say, okay, 6 months, that's half a year, and just put 1/2 or 0.5 for your time, that kind of thing. Future value or final amount, accumulated balance, that's going to be A, is the total repaid at the end of the loan, or total value. So this includes both your principal, that you started with, the amount that's borrowed, plus all the interest. So this is principal plus interest. So if a problem is asking for just the interest, well, the future value, this final amount, future value, it's actually the interest plus the principal. You can always get the interest if you just subtract the principal, and then you'll have just the interest left. If you just want the principal, that's what you start with. But the future value, this is both the principal plus all the interest that's accrued, that's occurred for this loan. So let's look at a simple example, simple interest. So Joe asked to borrow $5,000 to buy a car. He agrees to pay you simple interest, 4% per year. How much will Joe pay you if he pays off the loan in 3 years? So he's borrowing $5,000. That's going to be our principal because that's how much we borrowed. Simple interest rate is 4% per year. This is going to be our APR because it is a per year, yearly interest rate. And 3 years is how long for this loan, so time. So we're just going to put these in. We're going to have our principal, 5,000. Our APR of 4%. Be careful though, when we're working percents, we want to remember that we need to use these in decimal. All the formulas we're going to be using for this are going to be needing the APR to be in decimal form. So this one we're actually going to put 0.04. Remember, to get this to a decimal, I have to move the decimal. It's typically right here after 4. It's like 4.0 or 4. We move it over 2 spots to get 0.04. That's the decimal version of the number, and that's what we're going to use in our equations. And our time, T, would be 3 years. So we put this in our formula. This little formula will give us the final amount, how much it's worth after 3 years. So the principal of 5,000 times 1 plus APR, which is 0.04, times 3. It's supposed to be times. In this formula, you notice we have this 1 here. What that does is that just makes sure we include the principal, because you do 5,000 times the 1, you've got the full principal. And then 5,000 times this 0.04 is going to give us the interest. And we want 3 years worth of interest, so that times 3 does that. So this basically is just a quick way to get the principal plus the interest. We'll grab our calculator, throw that in. We have 5,000 times parentheses 1 plus 0.04 times 3. Close that off, and that should give us our amount. And it should be more than 5,000 because we started with that for principal, and it is. It's 5,600, which is a reasonable amount for 3 years worth of interest at a nice 4% interest rate. So we got 5,600 for that amount. All right, so that's simple interest. Here they're making, about $200 a year off this $5,000, and then they do that for 3 years. So they end up with to go with their $5,000 of principal on this. Now, simple interest only charges interest on the original principal, but most of the time nowadays people do compound interest. Compound interest charges interest on both the original principal and on the previously accrued interest. So basically the idea is, that first year you are earning interest and you weren't charging interest on that interest the next subsequent years. When you did simple interest, the first year you earned the same amount of interest as you did year 2 and year 3. Bankers looked at this as, well, if I loan out that amount of money for a year and get repaid in the first year, then I can take my principal plus the interest I earned, a whole year's worth of interest I've gotten, and I can go loan it to someone else, and now I'm going to be able to make more money because I got my loan repaid, quickly after the first year, and I could go make more. So that's going to be this new idea, compound interest, where bankers say, I don't want to wait till the end to do my compounding, to figure out the interest. I want to figure it out, periodically, like every year I want to calculate the interest, and then I want to add that back into the principal so the next year I can earn more interest. So, for example, in year 5, your interest would be charged on both the principal, the starting amount that we started with, but also the first 4 years worth of accrued interest. And so you'd be making more interest. So let's look at an example that deals with that. So back in 1461, quite a while ago, Edward IV borrowed $384. Not a lot of money to borrow nowadays, but maybe back then it was a bit more. From the New College of Oxford. The king paid back part of it. He paid 160, but he never repaid the remaining balance. So then, in 1996, New College rediscovered the debt and wrote the Queen of England asking for repayment with interest. Kind of bold. I don't know if I'd be willing to write the Queen and say, hey, you owe me money. Assuming an interest rate of 4% per year, it was calculated that the college was owed $290 billion. Was the calculation correct? Now, if we did simple interest with this, if we were just doing simple interest, first off, note that the principal in this case, well, it started at 384, but they paid back 160. So they actually never paid the 224. So the principal is actually the 224. One of those fun times in a math problem where they give you 3 different numbers, you got to pick out which one actually matters. So it's actually this one, because that's the remaining balance. They borrowed 384, but they paid part of it. So the 224 is actually what matters. Time frame here, notice that they borrowed it in 1461, but they didn't, and they found it in 1996. So to actually find the time frame here, we're going to have to subtract that and figure out how long that time frame was. So 1996 minus that 1461 tells us it's 535 years. So a pretty decent amount of time. 535 years, that's going to be our time frame. And they did a pretty reasonable interest rate, 4% per year. That's about like inflation is typically 4% per year. So it's not that unrealistic of an interest rate. So 4%, so the APR would be 4%, and again, we want to turn that into a decimal, so we'd actually use 0.04. If we did simple interest with this, if we did our simple interest, we would just be waiting until the end of 535 years and saying, okay, that $224 has earned 500 years worth of interest. Let's see what that gives us. So we do that. Final amount is equal to principal, which is 224, times 1 plus the APR, which is 0.04, times this 535, and it would give us the simple interest on this. So how much we would earn, after 535 years. So we do that 224 times parentheses 1 plus 0.04 times 535, and it actually ends up being about $5,000. Nowhere near that 290 billion. The difference is they weren't calculating simple interest. They weren't saying, okay, we'll wait till the very end and then calculate the interest. They were doing compound interest. They were saying, well, every year it earned some interest, and so the next year it earned more interest because it had the previous year's interest already. We included that when we charged interest the next year. We compounded. So the compound formula is a little different. It's similar here. Now, instead of multiplying by t, we'll see that t becomes a power. And that's what happens when you're doing compound interest, because you do this calculation t times once for every year. So you're multiplying principal times 1 plus APR, a bunch of times. In this case, we have 535 as t, we end up doing 535 times. So we still have the same principal, 224. 1 plus 0.04 is still our interest rate, but now the 535 is actually our power. And this does compound interest. So we're calculating the interest every year, and we'll see the difference there. So let's go ahead and type in 224 times parentheses 1 plus 0.04. Close that off, do power 535, and we get pretty big number. So you get, it looks like 2.9, but it's actually got this times 10 to the 11th here, and that times 10 to the 11th means that we actually have to move this decimal over like 11 spots. So if we do that, we count, so we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We end up with a number here that's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All these, I'm rounding, all these zeros to it. And you notice that, of course, you have your thousands, millions, and billions. This is $290 billion. So they're not wrong. 290 billion would actually be a reasonable amount versus, that amount back then. I doubt they're really going to get the money. That's probably, not going to happen in the long run of the scheme of things and all that. But that's how money grows, with compound interest. This is really essential to our modern world of finance and banking. If you work in business at all, with money at all, compound interest like this is king. This is just such an important thing. You can see the difference between someone that doesn't charge compound interest, someone that just gets the interest at the end. They only made, $5,000 versus someone who compounds makes 290 billion. This is why any banker or any business person, you walk up to them and say, would you rather have $100, today, or would you have $100 in a week from now? And they would all say $100 today, because they could take that, they could invest it, earn this compound interest, and they'd have a lot more money in a week than they do today. Maybe not a lot more, but they'd have more. That's the idea. So compound interest is really important. So we're going to spend the rest of this section dealing with compound interest. And it's going to be a key component also for later sections as well. So the New College case demonstrates how much money can grow with compound interest. It's a form of exponential growth. Same kind of thing that when like viruses propagate or bunny population growth, it's that exponential growth where things are just getting larger and larger, kind of a snowball effect where the snowball rolls and gets bigger and bigger. So here this chart shows the growth of that $224. You start off at year 0, it's just $224. And the first 20 years, you can see that there's actually not a lot of growth. It kind of stays pretty level. But as it grows, you can see that the curve gets steeper and steeper. And so the increase gets better each year, because each previous year you're adding a little bit more interest. So the first 10 to 20, there's not a Once you get past 40, you really start to go up that curve, and you can really see it getting steep. And even just in the first 100 years, we're not looking at 500 years, we're just looking at the first 100 years, you can see it's already getting pretty steep. It's already in the tens of thousands because of that steep growth curve. So this is why compound interest is so important, because you can climb this curve. It takes some time to do it, but the more you can climb the curve, the better. And also, the higher your interest rate, the steeper this curve is going to be even at the start. 4% is not that high for an interest rate. So if you're at the 8 or 10 or 12%, you're going to see this curve even steeper to start with, and that's going to grow a lot faster. So let's look at an example kind of shows how this compounding works and how it makes things grow so quickly. So George is thinking about putting money away for retirement. He's currently 25 and he plans to retire when he's 65. He can either invest $6,000 at 7.5% APR now, or maybe he could wait till later. Maybe he's going to use that money for now and he wants to wait and he'll just start investing when he's 45. He'll do the same amount, same interest rate. He wants to know, is it really worth putting the money away now versus later? Like, does that make a big difference? So first off, let's look at, 25-year-old George and think about what's going on. We'll say when he's 25, well, if he's going to invest at 25, his time, since he's waiting until he's 65 to retire, is going to be 40 years, right? We just do that, 65 minus 25, and we get 40 years for his time. He's doing, for his principal, that's 60,000 or 6,000. And his interest rate, or APR, is going to be, in this case, 7.5%. You move the decimal 2 over, you get 0.075. So using that interest formula, A equals P 1 plus APR to the T power, using that with these values, we can figure out how much money he's going to make if he does it this way. So his principal will be 6,000. That's how much he's borrowing or investing. 1 plus APR, which is 0.075, and because he's invested when he's 25, he's going to have 40 years of investment. And we'll see how that works, how much money he has saved if he does it that way. So for that, we get 6,000 times 1 plus 0.075, blows that off to the power of 40 years until he retires, and it would turn into 108,265.43. I don't really need the decimals, pennies. I'm sure he's not worried about that when he's looking at $108,000. $108,000, and that's if he retires. If he invests that now and just lets it sit for 40 years, he's got $100,000 when he goes to retire. Now, maybe instead of doing it now, he says, well, I'm going to wait till I'm 45. So let's look at, if he's 45 doing the same thing, and he's thinking, I'm going to wait a little bit. So the only difference here is now his time frame is going to be, what, 20 years? Because 65 minus, 45 is the way he saves it. He gets 20 years. So it's the same equation, still 6,000. Still 1 plus 0.075 to the 40th power, 60th, 20th power, 20th power, 20th power, because our time is different. That'll give us his amount. So the big difference here is the time, right? That's the big difference. I don't know why I messed that up. The big difference is that instead of doing it now and having 40 years for it to grow, he's going to do it later, so it's only going to have 20 years to grow. On this TA30 calculator, if you don't want to retype the entire equation, you use the little up arrow and get to your equation, hit enter, and then it types the equation, and you can go back and edit. So like something like this, I could replace the 4 with the 6 just by, or 2. I don't know why I wanted to go 6. Type a 2 over top of it, and there we go. So now I've got the equation with just 20 instead of 40, and we can see the big difference there. So now instead of 108,000, he'd have 25,487 less, right? Because he hasn't given it that time to grow. This is why people, if you talk to people about saving for retirement, one of the big things they'll tell you is start doing it early. Don't wait until you're getting older. People that wait till they're like in their 40s and 50s and then start thinking about retirement, they have a lot harder time saving for retirement because they're not able to use this exponential growth. They spend, if you wait till you're 40, 50, you only get 10 to 20 years. But if you start doing it when you're in your 30s or, younger, then you get to climb further up this curve. And, look, this impressive right here with this 4%, but I think if you got a higher percentage, you'd see it's even more important to get in that early range. The longer time frame you give yourself, the more that money can grow. So that's why, investing young is better. So we'll say yes, it's probably worth investing now. It's a large difference. This is like 4 times what you would have made otherwise. Um, so in real life, most people don't just put one sum of money away and say, that's my whole retirement. That's not really realistic. Most of the time we kind of make payments over time, and we'll actually get to that later in this unit. But this is just a good example to show you the difference that time makes in these problems. Okay, the graph below shows that same $224, but now we're looking at the difference between investing at 4% and 2%. And this is a good way to show you how the interest rate has a really large effect on the growth as well. So the graph illustrates, a small change in interest rate can really make a big difference. So that 4%, you can see how by 100 years it's really climbing up high into the tens of thousands. But 2% being half as much percentage, being a smaller percentage, it's not growing nearly as fast. By 100 years, it's still down here in maybe the hundreds of dollars. I don't think it's climbed up to the thousands of dollars. So interest rates are a really big thing when you're looking at loans and stuff like that. The higher interest rate, you're going to pay a lot more money. A lower interest rate, you're really going to save some money. So let's look at an example where that's what happens, where someone saves money by getting a better interest rate. So when buying a home, there's a possibility of purchasing points. We'll actually talk about points more with the mortgage project as well. So points are something you want to make sure you pay attention to. Points reduce the interest rate on your mortgage. So basically, you pay a fee for these points, and you earn these points, and they lower your interest rate on the mortgage. So John's considering one of these purchases. He could either borrow $150,000 for his mortgage at 4.75%. And it's a 30-year loan, which is typical for homes. Or he could pay $5,000 extra to purchase enough points to reduce his interest rate to 4.55%. I don't believe the $5,000 goes towards your paying off your house. It's just a fee you're paying, and they give you a little bit better interest rate. I might not be right about that because I'm not a home expert. That's something you definitely want to talk to with your mortgage financer and stuff. When if you go to buy a home and do points. But points are a way to get a lower interest rate. So he's looking at two options. He can do, a price with no points and have 4.75% interest rate, or he can pay 5,000 points for points and get lower interest rate. So we'll do it both ways. First off, we'll just say, well, what if he just is buying the house? He's got $150,000 he's got to borrow, 4.75% interest rate, 30 years. So if he doesn't pay for any points, no points, how much is he going to pay? Well, here, $150,000 is going to be our principal. His interest rate, or APR, is going to be 0.0475, and his time frame is 30 years. The actual calculations for paying off a house are a little bit more complicated. We'll get into those later. But for now, let's just make it simple and figure out, using this principal, APR, time, let's say, using our formula, A equals P 1 plus APR to the T power. Let's figure out how much you'd actually have to pay back. If you waited till the end of 30 years and paid it all back at once, it's a little high because in real life you kind of pay as you go. You don't wait till the end of 30 years. But this will give us an idea of how much the points could save them. So we have 1 plus 0.0475 to the 30th power. Okay, so if he borrows for the house and he waits till the end of 30 years to pay it off, which isn't realistic, but that's okay. We'll give us kind of an idea. 1 plus 0.0475, close that and do the power of 30. So how much would that loan be worth? Well, it'd actually be worth $603,548 because he's using that 0.0475 interest rate. So really a lot of money. Again, in real life, it's not quite so bad because you kind of pay off as you go. But if you waited to the end and then paid it all back at once, yeah, it'd be over $6,000. So let's try it again, but this time let's use this 4.55%. So how much could he save if he could just lower that from 4.75 to 4.55? So the same formula, the only difference here, besides the principal and stuff will be the same. The only difference is this interest rate. So now we're going to do 0.0455. Again, moving the decimal 2 spots gives us that 0.0455. Still a 30-year loan, still $150,000 for the loan. We want to see the difference here when we change the interest rate. I'm going to go back and use that enter trick on my calculator so I can get that retyped. And then I can just change this from 4.75 to 4.55. So change that to a 5. So now it's ready to type 569,917. 99. I guess you could bump that to an 8 because that's, if you're rounding. Always watching my math out and stuff and do problems. You don't want to run to the nearest dollar, nearest penny. Be careful of that. But a lot of times they'll say cent because cent refers to the penny. So it's the second decimal place. But we'll notice here, yeah, that's about $30,000, a little bit more than that in savings just by getting a lower interest rate. So yeah, he had to pay some extra money up front now, but he saved quite a bit. Saved over 30,000. That's really big savings. So, is it a good investment? Well, yeah, because this $5,000 now could save him $30,000 over the next 30 years. You can save a lot of money if you can lower your points. If you can find a mortgage that's a little bit lower interest rate. That's why people always tell you to go shop around for mortgages. If you ever look into buying a house, one of the big things they'll tell you is if you can find a house where you can get it with a little bit better interest rate, a little bit better mortgage rate, you can save a ton of money. And it's because of this whole compound interest thing. So if you can, find one that's 4.55 versus 4.75, as long as you trust the lender, the person's going to lend you the money, do it. Get a lower rate, and that's going to really make a difference. Okay, now so far I've been doing compound interest on a yearly basis, where they wait till the end of the year. Now bankers pretty quickly realized that waiting till the end of the year was silly because they could do it, partway through the year. They could calculate the compound interest partway through the year, and they could actually make a little bit more money because when you're compounding more frequently, you're going to have better growth. In fact, it's really hard to find anything anymore that does yearly compounding. It's not very common. Even like your savings in a bank account, that compounds monthly because at the end of each month, the bank pays you the interest that bank account's earned, and it goes back into your bank account. So your savings account actually is a monthly compounding type of situation where you calculate the interest after each month and put it back in. Now, to do that, we're going to use a slightly different formula. This formula is actually going to be on your formula sheet. That yearly compounding formula is not, because it's just not very common. In fact, if you want the yearly compounding formula, you can just make this N1 in this situation, and this formula will be that same thing because there's the 1 plus APR, then the T for the power. This N here is basically how often you compound each year. So the N is the number of compoundings per year. So if N is 1, then that's just once per year, and that's yearly. So that's why we don't have a yearly formula on the formula sheet, because you can just use this formula. If you want to do yearly, you just make N1. If you want to do other things, if you want to do monthly, N would be 12, because you'd be doing 12 times per year. So monthly would be 12. Daily, that'd be 365. Quarterly would be like 4 times a year. So like every 3 months you do it, 4 times a year. You could do semi-annually, which is twice a year, because that's every half year. So N is the number of compounding periods. What this does is it takes your interest rate. First, it divides it into pieces. You can't charge a whole year's worth of interest partway through the year. That's actually illegal. If you're a banker or investor and doing that, you can go to jail for that. You can charge, if you're doing monthly, you can charge 1/12 of the interest, so you divide by 12. Or if you're daily, you divide by 365. Or quarterly, you do 1/4, so you divide by 4. So we just divide into just a piece of that each time. But you're also compounding more frequently, not just doing it once a year, you're doing it periodically throughout. So that's why I also put the N in the power. So now if I'm doing this quarterly, I'm doing 1/4 of the interest, but I'm doing it 4 times as frequently and 4 times per year. Or if I'm doing monthly, it'd be 12 times per year, or daily would be 365 times per year. So that's why N is in both places. It basically takes that formula we've been using, the yearly one, and turn it into a formula that now you can use for any period, whether it's daily, monthly, quarterly, whatever. So let's look at the difference, how that changes. Again, more frequently compounding is actually going to earn you more money. So that's what we're going to see. So we're going to compound $10,000 investment at 6% interest for 10 years. And first off, let's just do it with semi-annually. So semi-annually, which means that our N is going to be 2, because we're going to compound twice a year. Semi-annual means every like 6 months or twice a year. That's semi-annual. Principal is going to be the 10,000. Interest rate is going to be our APR, is 6%, and 10 years is our time. This formula now, we're going to find out what we get. So principal 10,000, 1 plus APR. Remember, 6%, turn it into a decimal, so we get that 0.06. So 0.06 over n, which in this case is 2, because we're doing it semi-annually. And then the power, we're going to have 2 times the time, which is 10 years, so 2 times 10. Be careful with these. When you go to type these in your calculator, if you don't put parentheses around the powers, it might try and take the whole thing to the second power and then multiply your answer times 10 instead of doing to the 20th power. If you can do the multiplication like 2 times 10 in your head, that might be better than having to, you don't have to worry about parentheses if you just put 20 instead of 2 times 10. But some of these are not easy to do in your head, so sometimes I'll have to put the multiplication in here or type in a calculator. So I just do the multiplication and put parentheses around it. So that's how I would type this in, just to be safe. Calculators, they're all a little different, so it's going to depend on your calculator. But most of the time, if you type it in with parentheses around the power, you're good to go. So we have parentheses here for the 1 plus my APR, which is 0.06, divided by 2 for the n. Close that parentheses off, do my power button. It's a little up arrow over here. If you didn't see, that's the up arrow down here is the power button. The power parentheses 2 times 10, and close that. So by putting the parentheses around that power, I know that the power is all going to be treated as a power, no matter whether my calculator looks like this or looks different. It should work. And we should get about $18,000. So by compounding semi-annually, if we're having this money for 10 years, we get $18,061 and 11 cents. Now what happens if we do the same thing, but now we compound monthly? Well, monthly means the n is going to be 12, because we're going to be compounding every month. So we're going to have the same formula for principal, 10,000, because it's the same amount. We have the same interest rate, 0.06. That's not changing. But down here, we're going to put 12, because now n is 12. And our power, we're going to have 12 times 10, or you could have 120. So that's the big difference here, is that 12 changed. So let's go back and do the same one. Now, if you have a problem like this and you want to actually reuse what you already did, you could still do that. But to get a number in front of the 2, to get like a 1 there, what I'm actually going to do, I'm going to hit second, and then I'm going to hit insert. And then it's going to give me this little floating cursor thing. And so I can press my 1, and you can see how it goes in front of the 2 now. It's not over top of it. Because if I had just gone in there and tried to type, the 12, type 1, it would go over top the 2. So to get it in front of it, I have to do second, insert, and then I can type the 1 in front of there. So now I've got the 12 there instead of the 2. So that's better. That's what I wanted for monthly. And you can see I made a little bit more money, right? $18,193.97. So the cumulative balance, I've made about $130 more, a little bit more than $130, just by compounding more frequently, by doing monthly compounding. So you can see why nowadays it's hard to find, yearly compounding, because if you're a banker, an investor, you're putting money out there and you want to make it grow with compound interest, you're going to really push for compounding more frequently, because more frequent compounding ends up with a little bit better growth, more money coming in, when you make those investments. Now, eventually, bankers said, well, I want to just make even more money, because compounding monthly is great, compounding daily was better, but I want to do better. And so they went on and they tried to figure out how can we compound even more and more frequently. What happens as n gets bigger and bigger and bigger? We'll start compounding like every hour or every minute or every second. Well, eventually, hiring some mathematicians, because the bankers had money that could do that, they found some mathematicians and said, okay, let's figure out a way where we can compound what they call continuously. And that means that you're just compounding every single moment, every day, all year long. There's no breaks. It's not like, oh, I waited a second or a minute or a day before I compound it again. So to do that, we use continuous compounding. Back in 1683, so this has been around for a while, Jacob Bernoulli discovered the value E, which is used to calculate continuous compounding. It's kind of like pi, where the value E is one of these infinite, non-repeating decimals, one of those numbers that goes on forever and ever and ever. We don't really like to round E. It is about 2.7, but pi you can get away with doing like 3.14. Most of the time that's good enough. But E, if you round it too much at all, it can really make your answers wrong. So we're not going to round E. We're going to actually use a button on our calculator. we're going to use the calculator E button. And this is the formula we're going to use. So it's similar to the other ones, right? We've had the P, the principal, we have the APR, the time. The difference here is you can see APR is now in the power, and E is in it. And this is the E. This is that about 2.78, the E amount. But we're going to do it by doing a button on a calculator. So the E button on most of these calculators, there's going to be a little E. So a lot of times it'll have an X for a power, because most of the time when people use E, it has a power. So I'm going to hit second and then this E button. And if you would just put E to the first, you just get plain E, which is 2.718. That's about E. But most of the time we'll be putting E with some kind of power, and we'll type in the power and do it that way. So that's most of the time what we're going to do. Okay, so let's do this one. And it should say compounded continuously. I found the first mistake in one of my note sets. I'm sure they're going to happen more often because I do make mistakes too. But the cool thing about compounded continuously problems is they always have to specify that, because they can't just assume we're doing continuous compounding. So you're only ever going to use this formula when someone mentions something about doing continuous compounding. You see the word continuous and you're pretty much guaranteed to use this formula. So I should have had something in here saying, this investment, 12,000 at 6.25% after 20 years is compounded continuously. So it's going to say it's continuously compounded, so we can use this formula. Our principals will be the 12,000, our APR is going to be the 6.25%, and the 20 years is going to be our time. So using that, we can get the formula filled in. So our principal, 12,000. And P next to E means multiplication, so it's actually 12,000 times E, again that's going to be a button on our calculator, to the power of APR 6.25%, with the decimal 2 spots to get 0.0625, I always get the decimal form, and then times 20 years. So times 20 years, that's going to be our calculation for continuous compound. So 12,000 times, we hit second, E, my parentheses to make sure my 0.0625 times 20. Multiplication happens inside the power like it's supposed to, and that turns into $41,884. Continuous compounding does make you the most you can possibly make with a loan, so you can't do any better than continuous. If I'd done this with monthly or yearly, I would have made a little bit less. It's not going to blow it completely out of the water. It's not like it went from I made 5,000 to 41,000. It's just going to be a little bit less if you compound monthly, but it adds up. And if you're a banker giving all kinds of loans year after year, if you're an investor doing that, the more you can do continuously compounding, continuous compounding, the better you're going to be with making more money. So that's what people shoot for. So now if you go get a home loan, a car loan, your school loans, those are all compounded continuously. So that's the best the bank could do. That's the most money they could make on those. Okay, now we've kind of seen how when you compound more frequently, the actual interest amount is higher. You pay more interest if you're the borrower, or if you're an investor, you make more money in interest. So that APR amount, the APR, is not the best number to use to explain how much money a loan is going to make someone, or they're going to have to pay. It can kind of get misleading because an APR is the yearly interest rate, but it doesn't count for compounding. So if you don't compound just once a year, if you're doing more frequently, monthly, daily, stuff like that, the APR becomes kind of inaccurate. It's not actually very good value. In fact, if you go and you look, where I'm in Rapid, there's signs for banks, and they don't usually post the APR. Sometimes they do, but most of the time they actually post what's called APY. And the difference between APR and APY is APR is just a straight interest rate. It doesn't care about how frequently you compound. APY is actually an interest rate that's adjusted to reflect your compounding. So it looks at how frequently you're compounding, and then it includes that in the calculation. So the more frequently you compound, the higher the APY is going to be, up to the max you can do when you do continuous compounding. So if you have like an APR of 7%, but you're compounding like monthly, your APY is going to be a little bit higher than 7%. It might be like 7.2 or 7.1. It's not going to be a lot higher, but it's going to be a little bit higher than 7%. And that's going to, in the APY, that's reflected, that's shown. So actually, it's one of those things where our government actually has made regulations to say that when banks go and publish their loans and their information for loans, they're required to share the APY and not the APR, because the average Joe doesn't know the difference between the two. And the APY is going to be a higher interest rate, and so then the average Joe is going to say, "Oh, well, this loan costs more," and they'll catch that because the APY reflects that, versus the APR wouldn't. So we're going to calculate APY. We're going to find APY. APY only really depends on the interest rate and the frequency of compounding. That's all you need. So I'll kind of show you how, if you have that much information, you can find APY. But first we'll do one where we give ourselves more information. We'll do one where we have the principal, we have the APR, we have the compounding period, and we'll figure out what APY is. And we'll figure out how to find APY. So again, APY, annual percentage yield, it's an interest rate, but it's dependent on more than just the APR, the yearly interest rate. It uses more than that. So here we go. We have an investment of $4,000. We have an APR of 9%, and we're compounding quarterly. That means our N is 4, right? Because we're doing it 4 times a year. We're compounding the interest. We need to go and find the APY. The formula for finding APY is just like this: is the annual interest payment divided by the principal. We have the principal. That's been given, so that's been nice. We don't have to worry about finding that. But we do need to find the annual interest payment. That means 1 year's interest. So the annual interest payment, I call it AIP, annual interest payment, is 1 year's interest. Now to find that, we have to take this loan, we have to figure out how much interest it's going to make in a year. So we have to go back, we have to find its value after 1 year. So we're going to use time as 1 year. We're going to do time as 1 year because we want to find a yearly interest payment. We're going to take our principal we have, our interest rate we have, our compounding quarterly, and we're going to find that. We're going to use that compound formula, P times 1 plus APR over N to the NT. This is for the compound interest when you're compounding more than once a year. We're compounding quarterly, so we have to use this formula. And this will help us figure out what 1 year's interest is. So using this formula, we have our principal of 4,000 times 1 plus our APR, which is 0.09. Turn this percent into a decimal, so 0.09, over N, which is 4. The power of 4 times 1, because we're just doing 1 year in this case, because we want just how much it's worth after just 1 year. So let's plug that in our calculator and figure out how much we're going to have after a year. So 4,000 times parentheses 1 plus 0.09 divided by the quarterly 4 times a year. Close the parentheses, power, and you could do parentheses 4 times 1, or you could just say, well, 4 times 1 is 4, so let's just put 4, because that makes sense. So why do parentheses and multiplication? I could just say, well, 4 times 1 is 4. We can do that in our head. So we get 4. 4 is the power. And that gives us $4,372.33 if you round that appropriately. The 3 leaves that one alone. So, when you're trying to round that, the 3 just leaves it alone. Now, this isn't just interest, though. This is the final amount. So this is principal plus interest. And we just want the yearly interest payment. We want to know how much they made in interest. So I'm going to subtract the $4,000 we started with, because that was our principal. And we're going to see that the interest payment is $372.33. That's our annual interest payment. So when you're doing AYP, or APY, when you're doing the annual percentage yield, you're trying to find, APY. You need to know how much interest they make in a year. And the first year they're going to make $372.33. That's the interest made in a year. And so to find APY, we're going to take that yearly interest, that $372.33, and we're going to divide it by the original principal. We're going to divide by that $4,000. And that will give us, that'll give us how much the APY is. And because we're doing more than yearly compounding, we expect this to be bigger than that 9% we started with. APY is good. It's adjusted for compounding. The more frequently you compound, the more it goes up from your original amount. If you compounded, less or just compounded yearly, then this wouldn't go up. But anytime you compound more than once a year, your APY is going to be higher than your APR. So let's try it. Let's do 372.33 divided by 4,000. And we get 0.093, but remember that's in decimal form, so 0.093, which turns into 9.3%. That's our APY. So if a bank goes around and says, hey, I have a 9% loan, that sounds pretty good, but then when they say, well, it's actually 9.3%, that doesn't sound as good, but it's more realistic to say 9.3 because of that quarterly compounding. And they're not charging yearly compounding, they're charging quarterly, so they're actually charging you more than 9%. So that's why, legally now they have to publish this data. They have to say, hey, 9.3% is actually the rate for this loan because we're compounding quarterly. Though in real life nowadays, mostly banks compound continuously. So it'd probably be even higher than 9.3% if it was compounding continuously. Now, APY, again, really just depends on the interest rate you start with and the compounding period. It doesn't really matter what dollar amount, principal. If I did the same problem and I started with $2,000, I'd actually still get 9.3%. It wouldn't matter. If I started with $1,000 or if I started with $10,000, the APY is really just dependent on the quarterly, the compounding, and then the APR. That's all that really determines this percentage down here, which you can see in the next example problem, because in the next problem, they say, let's find the APY for this problem, and all they give us is the interest rate. So 6%, they say 6% is your interest rate, and the fact that you're compounded monthly. And that's all they tell you. They don't actually tell you the principal. Well, it's like, how are you supposed to use this APY formula and find the principal if they don't even give it to you? Well, the trick is that it doesn't matter. You can pick any principal you want, and you're still going to get the same APY, no matter what principal you start with. So on a problem like this one, that's what I'll do, is I'll say, I want to pick a nice, easy number, one number that I can work with. I don't want to get too small. Like $1 can actually get kind of confusing because you get really small decimals and stuff. So I usually pick something nice and easy around like 1,000 or 100. I'm going to do 1,000. So let's pick P equals 1,000. And it doesn't matter which one you picked. If you started with 1,000 or if you started with 100, you'd come out with the same APY at the end, no matter what. Then using this, I'm going to do that same formula again. We're doing compound interest, so P times 1 plus APR over N to the NT power. Here, N is going to be monthly, so it's going to be 12. My APR is 6%, so 0.06 is my APR. And we picked 1,000 for our principal. And again, when you're doing APY, we always want to find an annual interest payment, which means we want that to be yearly. So T is going to be 1. And that's what we're going to do on these. So using the formula, we have our principal, $1,000, times 1 plus 0.06 over 12. The 12 times 1 power, and that'll give us how much this is going to be worth after 1 year. So $1,000 times parentheses 1 plus 0.06 divided by 12. So hopefully you can see that a little bit better. Divided by 12. I'm doing my power button. Parentheses 12 times 1. Or you could have just put 12. I don't know why I put parentheses 12 times 1. I could have just typed 12. But that gives us, after 1 year, we're going to have $1,061.68. So $1,061.68. Rounding to the nearest penny. So rounding just to the second decimal spot. The 7 makes it go up. That's after 1 year. We subtract the $1,000 that we started with. So that's our principal. And so we end up with an interest payment of $61.68. That's our interest. So now that we know our interest, again, that's 1 year's interest. This is AIP. And we know our principal because we picked one. Right? That's how we got the principal. We can find APY. They're dividing that 1 year's interest, the $61.68, by the original principal we started with, which is 1,000. And that'll give us our new and more correct interest rate. So we're going to do 61.68 divided by 1,000. And we get 0.06168. So 0.06168 which if you turn it into a decimal, a percent becomes 6.168%. My math, I would usually have you tell you what to round to, so they might say 1 decimal place or the 10th place. I've kept all the decimals just because. But you can see how this is higher than that initial 6%. We compounded monthly, and because we compounded monthly, our interest rate went up. It almost, not quite 6.2%, but 6.16017 if you want to round it, is higher. We're paying more interest. Again, if you go to publish this, the bank's not going to publish that it's a 6%. They're going to publish it at 6.168. That's kind of required now by regulations. So they're not being quite so hopefully deceptive if they publish this little bit higher rate, the APY, that's adjusted for that compound. Okay, last page. One more thing to cover. So sometimes when you're doing these interest calculations, compound calculations, sometimes instead of trying to find out how much something's going to be worth at the end, sometimes you want to go backwards. You have some kind of upcoming large expense, large purchase, and instead of borrowing money at the time, you might want to save up and have more money when it happens. You might want to save up for your down payment for a house. You might want to save up for a car in the future, something like that. So sometimes what you're actually trying to find is how much I need to start with to get to a certain value in the future. So in problems like this, we're going to actually not know our principal. We're going to know how much we want to have. So you notice in this problem, we say we plan on buying a house in 10 years. That's our time frame. So we know how long it's going to take. We know we would like to have $50,000 to make a down payment. So this isn't how much we have now. This is what we would like to have. Would like to have $50,000. That means that it's not our value now. It's our future value. This is the amount we want to have in the future. This is the final amount we want to have to go make that down payment. Assuming you make no deposits in the account after the initial deposit, this is just a one-time deposit. Everything we saw in this section was one-time deposit. Next section actually cover when we make multiple deposits. For the amount described below, how much would you have to deposit now? So deposit now, that's your principal. That's what we're looking for. What's the principal? To reach your goal. This is an account with daily compounding, which tells us that N is 365, compounded daily, an APR of 8.5% or 0.085. So using this formula, the one we've been doing, the A equals P times 1 plus APR over N to the NT, you can see that we have everything here now except for P. We have the final amount. We have the APR, we have the N, we have the NT. We don't have the starting amount. So we need to go back and we need to figure out how much they want to start with. That's what we're looking for. So what we're going to do here is we're going to plug everything else in that we have. We're going to plug in 50,000, but the 50,000 goes on this side because it's the final amount we're trying to get to. It's not the starting amount. We're not starting with 50,000. If we had 50,000, we wouldn't have to worry about it. We just have a down payment. It's the amount we want to get to. P is what we're looking for. We want to know how much we had to start with to get here. And then APR is going to be at 0.085. N is 365. And the power is 365 times time, which in this case, we know we have 10 years, so times 10. So we want to figure out P. We got a little bit of algebra here. We're going to have to get P by itself. Now, before I do too much, I'm actually going to go ahead and just type this in because this will give me one big decimal. It's P times this number. And so instead of having to try and work with all this stuff, let's just make it a decimal number, make it easier to work with. So let's type that in first. So let's type in parentheses 1 plus 0.085 divided by 365, close parentheses, power, parentheses, 365 times 10. Close your parentheses. So I just typed that in, I got 365 times 10, I got the parentheses around my power. And I've got the 1 plus 0.085 divided by 365. This gives me 2.33. It's not my answer, it's just a decimal number. It's a little bit nicer to work with than having to type all this stuff or write all this stuff. So I'm just going to write down this decimal. I'm going to keep a lot of digits. In fact, I'm going to keep every digit I can because I don't want to round too much now because I'm not done with the problem yet. But I just basically turn this big parentheses with powers and stuff into just a decimal. So I just have P times that equals 50,000. So now it's really easy to see how to solve this. With algebra, we know that we can undo multiplication by dividing. So I'm just going to divide both sides by this 2.3394153336. You know, that number. The divide and cancel out. I have to divide it to both sides, right? You know that when we're doing dividing to solve an equation, you always have to do both sides. So on this side, they canceled. Here we get P just by dividing these numbers. So I can take 50,000 and divide it by that number. Now there's a trick you can do on your calculator. You can type the 2.33 with all those decimals, or what you can do is you can actually hit the second button, and then there's this little A and S down here. That stands for answer. And so it's actually going to use the previous answer. So this 2.3394, which was the answer for the last problem, that's what it's going to divide 50,000 by. So it's kind of a nice little trick. If you don't want to retype that, you can use the little A and S. And now it's dividing like we want it to do. You know, if you had divided that by 2.3394, you'd get about the same amount. Maybe a little bit different for rounding, but about the same. So either way, you get $21,372.86. So this is the money we'd have to put away now, so that in 10 years we would have $50,000 for that down payment. The big thing here to notice is that the amount they gave you up here is not your principal. It was the amount they wanted to have in the future, not the amount they have now. And I think that's where people really get stuck on this problem. You know, you'll see this in the homework. You might see something like this on the quiz or the test. Really watch and notice when they give you the amount and say, this isn't your starting amount. It's not how much you are borrowing. It's how much you want to have at the end. And that's why it's a final amount A, not a principal P. And so we did this that way. All right, that's it for this section. So we do mostly just with compound interest, learning how to use compound interest using the compound interest formula. You saw this compound interest formula is going to be the one you use the most because you used it here, used it with the APY calculations when you're doing compounded monthly or quarterly, stuff like that. We did also use the PE to the APR times T continuous compounding formula. Again, the word continuous will show up in those problems. That'll help you know that you're using that formula. And we did a couple with the simple interest. So you might see some simple interest stuff on your homework and stuff. We actually will see simple interest to come up also in the next section because there are certain type of investments that still pay simple interest. So that one we'll get back and we'll use that one as well again. So now you got the idea. Hopefully now you understand how important compound interest is. It's really a big part of our finance system, a big part of how people invest for retirement, all those kind of things. So hopefully you understand that and use that when you're investing as well. Thank you, and I'll see you on the next one.